Welcome to Math Zone African Motives. Today, we're diving into the world of algebraic graphs. Specifically, we'll learn how to sketch one of the most fundamental shapes in mathematics, the circle. Our goal is to understand the general equation of a circle centered at the origin and use it to sketch any such circle you encounter. Let's begin by defining the form of a circular graph. What is the equation that describes a perfect circle centered at the origin? The general form, or standard equation, of a circle centered at the origin is x squared plus y squared equals r squared. Let's break that down. In this equation, r stands for the radius of the circle. The radius is simply the distance from the center of the circle to any point on its edge. This equation is a direct application of the Pythagorean theorem. Imagine a right-angled triangle where the legs are the x and y coordinates of a point on the circle, and the hypotenuse is the radius r. Let's look at the diagram. Here we have a circle centered at the origin. If we take any point, x, y, on the circle, we can form a right triangle. The horizontal leg has a length of x, and the vertical leg has a length of y. The hypotenuse is the radius. By the Pythagorean theorem, x squared plus y squared must equal r squared. This equation holds true for every single point on the circle's circumference. For the purpose of your syllabus, the radius will always be measured from the origin, meaning we'll only be dealing with circles centered at the point 0, 0. Now, let's explore some key features of this type of circular graph. Understanding these features will help you sketch more accurately. First, a circular graph is a relation, not a function. Why is that? Because a vertical line can cut through the graph at two different places. This means for a single x value, there can be two corresponding y values. Second, the graph is continuous. You can draw it with one smooth, uninterrupted motion, meaning there are no breaks or holes in the line. Third, the circle is symmetrical about the x-axis and the y-axis. If you were to fold the paper along either axis, the two halves of the circle would perfectly match. In fact, it's symmetrical about any line that passes through its center, the origin. Fourth, let's talk about the domain and range. The domain is the set of all possible x values for which the graph exists. For a circle of radius r, the domain is the set of all x values between r and r, including r and r. Similarly, the range is the set of all possible y values. For this same circle, the range is the set of all y values between r and r, again including r and r. Finally, because a circle is a relation and not a function, it does not have an inverse function. A horizontal line can cut the graph more than once, failing the horizontal line test. Let's summarize. We've defined the standard equation of a circle centered at the origin, x squared plus y squared equals r squared. We've also discussed its key features, like being a continuous relation and its symmetrical properties. You now have the foundational knowledge to begin sketching. In our next scene, we'll apply this knowledge to some examples. Now that we understand the general form of a circle, let's put that knowledge into practice by sketching some graphs. We'll work through example 4.8 together. The exam tip is incredibly important here. Always write the given equation in the general form, x squared plus y squared equals r squared, to clearly identify the radius. This will be our first step every single time. Let's look at the first problem. We are asked to sketch the graph of x squared plus y squared equals 36. Take a moment to think about what this equation tells you. To sketch this circle, we need to find its radius. The equation is already in the standard form, x squared plus y squared equals r squared. By comparing the two equations, we can see that r squared is equal to 36. The general form helps us make this direct comparison. To find the radius r, we take the square root of both sides. This gives us r equals the square root of 36. Since radius is a length, it must be positive, so we take the principal square root. The square root of 36 is 6. Therefore, the radius of our first circle is 6 units. We have now found the key piece of information needed to draw our graph. The question asks us to sketch the graph, not just calculate the radius. So let's draw it. First, we draw a set of Cartesian axes. The circle is centered at the origin, 0, 0. Now, we mark 4 key points that will guide our sketch. These are the points where the circle crosses the x and y axes. Since the radius is 6, the circle will pass through 6 on the positive x-axis, 6 on the negative x-axis, 6 on the positive y-axis, and a 6 on the negative y-axis. Remember, these are just r and r. Finally, we sketch a smooth circle that passes through these 4 points. And that's it. We have successfully sketched the graph of x squared plus y squared equals 36. You can see how the graph visually confirms the radius is 6. Excellent. Now let's move on to the second part of the example, which presents a slightly different challenge. This time, we need to sketch the graph of x squared minus 17 equals negative y squared. At first glance, this doesn't look like our standard circle equation. Remember our exam tip? Our first step is to rearrange it into the general form. The general form is x squared plus y squared equals r squared. Notice the plus sign between the x squared and y squared terms. Let's rearrange our equation to match this. Our equation is x squared minus 17 equals negative y squared. To get the y squared term on the same side as the x squared term and make it positive, we can add y squared to both sides. This gives us x squared plus y squared minus 17 equals 0. Now, to get it into the r squared form, we need to isolate the x and y terms. We can do this by adding 17 to both sides. And there we have it. The equation is now in the general form. By rearranging, we've transformed the equation into one that clearly describes a circle. Now we compare our new equation, x squared plus y squared equals 17, to the general form. It's clear that r squared is equal to 17. To find the radius r, we take the square root of both sides. This gives us r equals the square root of 17. Unlike the first example, this is not a perfect square. The memo provided for this problem simply states r equals the square root of 17. This is the exact radius. However, to draw the graph accurately, we need its approximate value. Let's calculate it. The square root of 17 is approximately 4.123. This approximation, which we'll round to 3 decimal places, tells us the distance we need to mark on our axes. The question asks to sketch the graph with the exact value, so we will label our axes with the square root of 17, but we'll use 4.123 to help us position these labels on the number line. Just like before, we start with our Cartesian axes centered at the origin. Our radius is the square root of 17. So the circle will pass through the square root of 17 on the x-axis, negative the square root of 17 on the negative x-axis, the square root of 17 on the y-axis, and negative the square root of 17 on the negative y-axis. Again, using our radius approximation of 4.123, we know that these points will lie between 4 and 5 on each axis. Finally, we sketch a smooth circle that connects these points. You have now successfully sketched the graph of x squared minus 17 equals negative y squared by first rearranging the equation and then identifying its exact radius. Let's take a moment to recap what we've learned and look at the final visual representations of the 2 graphs we just sketched. We started by understanding the fundamental equation of a circle centered at the origin. X squared plus y squared equals r squared. We learned that the value of r represents the circle's radius. We applied this to 2 examples. The first was x squared plus y squared equals 36, which gave us a radius of 6. The second, x squared minus 17 equals negative y squared, required us to rearrange it first to find a radius of the square root of 17. Here you can see the 2 graphs side by side, exactly as they are presented in your notes. The first circle has a radius of 6, and the second has a radius of the square root of 17. The visual difference is clear. The first circle is larger, which makes sense because its radius is larger than the square root of 17. Now you are able to draw a circle with a radius of 6 and one with a radius of the square root of 17. You've also seen how to identify the radius from an equation in general form and how to rearrange an equation if it's not in that form. Great work! Thank you for watching this tutorial from Math Zone African Motives. If you found this video helpful, please subscribe to our channel for more tutorials. See you in the next one.